Very clear and bigger. All right. Excellent. So I think if it's okay with you, maybe we'll slowly get started. Again, thanks everybody for coming. We will watch the chat for everything from technical difficulties to, are you open during the seminar to questions along the way, as long as they don't interfere with the flow?
Yes, absolutely.
Okay.
As long as we have time, I'm open to questions.
Very good. So well, I'll kind of keep an eye on the chat, but other than that, if people either want to politely voice a question or ask a clarification, I'm confident that he will address it, and that'll make things better for everybody. But so introduction wise, Marcelo arranged this, and many thanks to him, but he got pulled away a little bit ago. So I'm just going to introduce Mani Jafari, if I pronounced that decently. He is an assistant professor of naval architecture and marine engineering and robotics at the University of Michigan. In Ann Arbor, he received his PhD from the Center for Autonomous Systems, University of Technology in Sydney, New South Wales, Australia in 2017. So hopefully he's had a fun climate change to Ann Arbor. Recently established the Computational Autonomy and Robotics Laboratory with research interests in theory and applications of robotics and autonomous systems. So with that, we're a fairly casual group. We have a lot of three types of people involved. So faculty, a good number of graduate students, and a good number of undergraduates. And so with that, unless you need anything else, we're a pretty simple group. We'll hand it over to you. And I assume at the end, we'll open it up a little bit more for broad questions and things like that. But thank you very much for joining by Zoom. And I'll mute now for a little while, okay?
Thank you so much for the introduction. It's great to be here, and it's a pleasure to present some of our work in Michigan to you. Full disclosure, I'm in Naval Department, but I don't know how to design ships. My colleagues know that very well. I do collaborate with them. I know how to build autonomous systems, work on some of robotics problem, but you will see that the platforms might be specific because of the examples we solved, but the mathematics and the methods are applicable to a variety of different platforms in form of different projects, of course. So today, I will just talk about a little bit about how modern approaches to data-driven methods for learning can be combined with a lot of knowledge that we have from geometry. And we've been using that historically for solving a lot of problems in robotics and control. So robotic systems, how, but first, why? So that's important to answer. We need robots because there are a lot of missions and situations that humans cannot operate, or it is too difficult for a team of humans to operate by themselves. For example, going into a fire, we can use a team of robots to collaborate with humans. Maybe we want to do scientific exploration in the wild, in the space. You're familiar with NASA missions at this point, and there are a lot of exciting examples on that. Maybe robots want to collaborate with humans in our daily lives, and maybe we want to inspect regularly some areas in offshore, onshore factories, and it's nice to have some systems that can just work 24/7 and perform inspection tasks. In particular, underwater inspection tasks is very dangerous for divers, and there's a lot of interest in marine robotics to perform those tasks autonomously. Environmental monitoring is always an interesting application for robotics. Now, what makes robotics unique in this aspect is that unlike other technologies, such as remote sensing, when we get images from satellites, robotics platforms are embodied intelligent machines that you can move. This mobility aspects of these machines will enable them to have smaller sizes and being able to move around and collect information and communicate. This is an aspect that is unique to robotics. We do not have it in more traditional engineering disciplines. Although there are common goals in science and engineering, as you know, that robotics, of course, share that with those disciplines. Now, I can talk about different platforms that we have in robotics, but I'm going to focus on legged robots because that's where our recent result is, and we have cool videos on that. So I'm going to focus on legged robots, but you can imagine a lot of these applications and methods are applicable to other platforms too. And we are working on some of those platforms like wheeled robots, autonomous surface vehicles, and so on. Now, what makes legged robots interesting is that they can traverse discrete terrains. Almost 70% of the planet is not traversable by wheels. And legs can navigate rough terrains. Also, legged robots are suitable for environments that are built for humans. Humanoid robots can navigate at homes, at factories. These environments are built for human. Therefore, it makes sense to have a robot that looks like us. So that's a big motivation behind building a humanoid robot. Although this robot is quadruped robot. At a very high level, if we want to talk about an autonomy framework, how to make a physical platform that has actuators and some basic movement capability autonomous. So what we need to do, we need to have a sensing capability on the robots. We need to have a bunch of sensors to measure, for example, the movement of the legs. These are encoders. We need to have maybe a camera, maybe another sensor that is called inertial measurement unit. We can measure the body acceleration and angular velocity. Now, humans have these capabilities as well. We can see, we have something like almost like a gyro in our ear. We can sense our orientation, and we can sense force and interaction with the environment as we walk and operate. So we have visually sensing, we have state estimation and world model. We need to have a perception of the surroundings so that we can plan and basically act. That's the control part of the robot. Today, I'm going to talk about mostly about the state estimation, and if we have time, about an example in planning. But we could talk about different aspects of this framework as well. And this is very high level. There are a lot of different modules we can talk about. So one fundamental problem in robotics is localization. And as part of that is the reckoning or odometry. The robot needs to know where it is located at any time with respect to some reference. Imagine an underwater application when you don't know the location of the robot can easily get lost. And then you will lose the vehicle. It can be expensive, and we can never recover that platform. Same thing that can happen for a robot that goes into the forest or fire. So a fundamental need is localization. And this is typically starts with a state estimator or observer on the robot. So what we need to do, we want to estimate the rotation, velocity, and position of a frame that is attached to the body of the robot with respect to some world frame, some initial frame that we fix and we want to track with respect to that. That can be the base for example, for your station, where you start the mission, or anywhere else that you decide. So how can we estimate orientation, velocity, and position online on the robot, and so that we can track the robot? Now, there are a lot of sensors that we can use for that. The easiest approach is probably using a camera. We can use a camera and using computer vision techniques to track the robot. But the problem is, what if it's dark? What if the environment looks like what you see here. It's foggy and it's smoky, and there are situations that we are in a perceptually degraded situation. So just relying on vision is not going to make our framework robust enough that we can operate for long-term missions in real world. LiDAR is another example. It's an active sensor, but when you have a smoke, you will get reflections. The above pictures is an example of a scene that these two sensors can fail. The point cloud return from the LiDAR is completely around the vehicle, and it's not even penetrating into the smoke. So a natural idea here is that what if we use proprioceptive sensors? Proprioception means internal. All the measurements are internal. It's got nothing to do with the environment. These are joint encoders sensing body acceleration, angular velocity, and contact with the ground. A particular nice feature of legged robots is that we can use the contact with the ground as a source of information. That makes it, in some sense, easier to solve a state estimation problem, although it makes the control of the robot harder relative to wheeled platforms. And we want to do this at a high frequency, 1000 Hertz, 2000 Hertz. This is an example of an MIT mini cheetah robot. This is a small quadruped robot. We added a backpack, a perception suite on the robot. It has an NVIDIA Jetson GPU. As you can see, the robot goes into off-road. The camera is tracking, but suddenly there are leaves in front of the camera, and then the vision system loses the track. Once you lose the track, it's hard to recover because there's a gap in the localization, and we don't know where the robot is at that point. So what happens when we drop the vision, this is just a quantitative version of that experiment, that the uncertainty grows immediately when we lose vision compared to the state that we don't. And that growth in the uncertainty means that we are uncertain about the location of the robot. And if this happens regularly and for long enough, then we lose the platform. When we use more modalities, here vision, inertial, and contact, now that we have contact information, even when we drop vision using the other two modalities, although they're proprioceptive, only contact and inertial, we can still track without seeing any growth in the uncertainty. So that's another feature of robotics platform. Unlike computer vision methods that you can have a handheld camera, these platforms are embodied. There are a variety of sensors, and we usually combine these sensors that goes under the name of sensor fusion or state estimation also. It's a name for that. So that justifies using redundancy sensing for solving a problem like this. Now, if you want to formulate this problem, you would go to do something like this based on the literature. We have, let's say, a bipedal robot here. We have the foot position that is in contact with the ground relative to the body frame, the torso of the robot. There's an inertial measurement unit, IMU sensor, in the torso of the robot. Using the forward kinematics, we can model and know the relative position and orientation of the foot with respect to the body frame. Then the standard approach in the literature is to use an extended Kalman filter, which is a filter that uses data to combine them over time and recursively give you an estimate of a quantity that you would like to know. And then we can basically estimate that orientation, position, and velocity. Now you might say, why we need to do this? Because these quantities are not directly observable. There is no sensor that you can have on the robot that tells you directly these quantities. So we need an estimation method to gain a knowledge of that using other measurements that are indirectly informing us about these quantities. And typically in experiments like this, we don't have GPS, we don't have an external source that can track the robot and tell us where the robot is located. Oh, that would be nice, of course, but we don't have that option here. Now, one fundamental problem for people who worked in this area, they know that a lot of these models are nonlinear. The original Kalman filter that was developed in 1960, it was for linear systems. Then it was extended to nonlinear systems, and people called it the extended Kalman filter. And the idea is that just linearize the system around your current operating point using standard calculus, Taylor expansion of your nonlinear model. And they use that linearized model to carry out the calculation. So what happens is, this is a very common way in engineering to solve nonlinear problems: linearize and iterate. What happens when you linearize, the linearized model often depends on the state estimate. Now, if the state estimate is partially wrong, or maybe it has large errors, that leads to incorrect linearization. Incorrect linearization leads to poor performance. And that creates a positive feedback loop. And that has been the problem for maybe 20, 30 years or so in this area, when people are trying to run these filters. It works if you have good initialization, but as soon as you're in a situation that linearization is not good, it might lead to divergence. So there is no guarantee for convergence. A recent result by Baru and Bonobel uses symmetry. I'm not going to dive into the mathematics behind it, but the high-level idea is that if all things equal and an object is located in the space, it should not matter where you start your movement, but what it matters is the relative movement that will accumulate error. So it doesn't matter if I start a delta movement here or you start a delta movement in Texas. The delta movement causes the accumulation of the error, not the absolute location of that object. So that's the basic idea. Now the question is how to capture this idea mathematically. And it turns out the right tool for that is using matrix Lie groups. And these are groups that model the geometry of the space. For example, in physics, the famous space-time model is using one of these groups for modeling the symmetry of space-time. For us, these are rigid body transformations. These rigid body transformations are the quantities we want to estimate. These are matrices, so we should respect the structure of the space. Longest story short, this will lead to a new definition of the error that we're not talking about it in details here. And that new definition of the error gives us a system that behaves just like the linear system. That was a breakthrough result, that now you have a nonlinear system using the right way of defining your error in the right coordinates. Now suddenly it behaves like a linear system. And in particular, it's log linear. So these models are log linear, or sometimes they call them linear exponential. So now using this new tool, we want to see how the system performs. So we have an IMU and contact and joint encoders. And if you derive the equation, it looks like something like this. Your linearizations are just constant. Unlike previous methods, this H matrix and A matrix, they do not depend on the state, and they're all constant. So that was a surprising result. Now we run this on a bipedal robot built by Agility Robotics. There's a LiDAR. The LiDAR is spinning 10 times, is returning 10 packets each every second, 10 times. You get point clouds, and in every point cloud there are 10 or more packets, and these packets are based on a rotating light beam. The problem is, as the robot moves and walks, these movements will make the point cloud distorted. What we do, we use this filter to estimate the robot orientation, position, and velocity, and then we use that to compensate these distorted point clouds. As a result, when we accumulate these point clouds from a LiDAR, for about 10 seconds, we're accumulating it here, we see a consistent map of the environment. Even though the robot is moving, the map is static. You can see that here. The staircase is static. This is a sign that the filter is working very well, and we have the correct estimate of the robot as it moves. And not only that, we can reconstruct what's around the robot, which is very helpful for navigation and interacting. And you can see the person is moving. We're not, if you're just accumulating point clouds, dynamic objects will leave traces in the map. But that's not for today. That's another story for robot mapping. Now this filter, as you see, it is completely based on geometry. It's a purely geometric method to solve this state estimation problem. Then we got another platform. This is MIT's Mini-CHEETAH. It turns out the robot doesn't have contact sensors. So that's a deal breaker, because if we don't know when the foot is in contact with the ground, part of the information we need is missing. So what we decided to do was, how about we use machine learning, deep learning, to estimate contact events. First, we did it in a supervised way, manually labeling. My unfortunate grad student had to sit down and label signals from the robot. But later, after he was done with all the data sets, he learned how to do it automatically. So then he ran automatic labeling. But luckily, he had ground truth labels labeled by himself, so he could verify that automatic labeling is doing well. So we have a method to automatically label contact events using signals that we read from the robot. However, it needs to look at a window of time that is after and before the event. So it's not possible to run it online. There is a delay in observing data and processing it. That's where the learning comes in. When you need information from the future to infer a quantity, but there is no time online to do that, we can collect data and train a model and then deploy it online. That will bypass the need for future information during deployment. So we could, it turns out deep learning, although it does not understand causality, it is purely based on learning correlation between input and output. It is able to learn the cycle of contact events for the given gait of the robot. So we run this network after optimization on the robot. It reads the IMU, acceleration, angular velocity, joint angle, joint velocity, foot position, and foot velocity in the body frame. And it will solve a classification problem that at any point, it will give us a label that whether each foot, we have 4 legs, each foot is in contact with the ground or not. Then we use the same previous filter to basically solve the same problem. And we collected the data, and this is publicly available. The code that I'm talking about is also publicly available, and you can try it. So we collected data on different types of ground because they have different contact features. So modeling contact is extremely difficult, but it turns out we can bypass doing that, in this case, using machine learning. So we run this experiment, Orbislam 2, which is a state-of-the-art for feature-based method for solving this localization problem. It fails at some point because the vision is blocked. The information is not coming in, and that system just fails. However, using this method, we can track in real time at 500 Hertz because the robot signals are coming at 500 Hertz, but we could in the lab run it at 1000 Hertz as well. So let's see a video. I'm going to speed it up. So the initial idea was purely geometric. Now suddenly we could use learning to estimate a quantity that it is very difficult to estimate it online, especially for this robot, because it's lightweight. Unlike heavy robots, we cannot rely on models and assumptions, dynamics of the robot to detect the contact. The legs are very light and it's very noisy to use model-based methods. There are a lot of details, but when a robot is in contact with the ground, there's foot bouncing, and this bouncing makes it even more difficult to detect whether this is a contact or it's just a touch. And I'm going to skip to the qualitative result. So we started in front of the robotics building in Michigan. If you haven't seen it, please come and visit. We have a brand new building, and it's a department now. We have a robotics department in Michigan. And this is right outside of the building. We have access to some forest-like area. Now, because we don't have ground truth, we overlaid the trajectory on the satellite map. And as you can see, qualitatively, it's pretty good. If you're running a mission and this is what you're seeing, you know where the robot is. It's okay if there's a little drift. Now, as soon as we did that work, then we thought that, well, now this is a framework that we have deep learning running alongside of a geometric method. What else we can do? Because it's possible to estimate so many other things using the same network or making it more complicated. So you can think about, maybe we want to estimate foot velocity, body velocity, foot acceleration, or friction. This is a good one, and it's very challenging. If you can estimate the friction, then you can operate in a lot of different situations. I know you don't see that on your roads, but we have icy roads here in Michigan, and you can send a robot and walking on ice, and it's slippery, and all the control methods will break down. And even self-driving cars are very interested in this problem. If we can estimate friction, then the controller can adjust their parameters somehow, and then that will maximize your comfort when you drive in different weathers and road conditions. So that's very interesting for cars as well, even though we study in the off-road setting. So it turns out we collected data already by knowing what's the ground type. So maybe we could classify and know what type of ground we're walking in using the same signals, just IMU, acceleration, linear angular velocity, linear acceleration, and kinematic information. And it turns out we can. This is just preliminary results. We are making it better, but just a rough attempt, it shows that it is possible to do that. So the robot can know different ground types. You could do a simple idea that the friction and if different ground type is maybe a known value, or a more advanced attempt will be to estimate it. However, it's difficult to model friction. That's already a problem for tires. So that's an ongoing problem. Some of us here are looking into it. So this was first part of it, and I'm going to connect it to more perception. See if you have. Somebody says that the Wi-Fi connection on campus is failing in C-STAT. I don't think this is related to the talk. I would contact authorities in Texas.
Yeah, well, we're checking on it.
All right, so now that you're all expert in state estimation for Lego robots, I'm going to talk about another idea that is still related to geometry, but I will connect it to learning, because these are unrelated, and seeing them in one place is what makes them exciting for a lot of researchers. So equivariant models are generally models that are symmetry preserving. For example, if you're looking at an object, this phone, from different views, it is very easy for us to say that this is the same phone. We have no problem with identifying these objects. Why? Are there a set of features that are invariant to the view that we're looking at this phone? Probably. So equivariant is a generalization of that invariance, meaning these features have the same orientation or translation, for example. But invariant means that no matter where we look at them, well, that's the same object. If we can find with descriptors features that possess this property, that makes it, for example, easy to detect a place. We want a robot to come back to a place and recognize it. That will allow us to detect the building, detect a new place, and being able to come back to maybe to where the robot started the mission. And a famous example of this is the 2D convolution. The convolutional neural network are translation equivariant, meaning if you run that on an image, the edges that you detect, for example, in an image will be the same, even if you shift the image to the left and right or up and down. That's not going to change the edges that you detect. So this idea is applicable to perception, planning, control, and in analytical mechanics and control, of course, it is known and heavily studied, but those literatures are not something that we used to it in computer vision and robotics. Now, to study this framework in a data-driven setup, where it's not based on model, but based on data, we can both look into kernel methods and deep learning. Kernel methods are the older paradigm of learning, and then came deep learning. They seems like it replaced it, but a lot of times you can combine them as well. So one example that I want to show you here, this is just an example of using that philosophy for building a framework, is that I want to solve a visual odometry problem, and I want to combine these point clouds by reconstructing the scene and tracking where I'm going. What are the challenges? Well, the point clouds that I read from these depth cameras are very noisy. There are, as the camera moves, there's part of the scene that is the same as before, but there's also part of it that is new. So there's partial overlap with different frames. Some scenes are textureless. If you're moving in an area that's just sand, it's just the snow, leaves, there is no particular pattern to track. That makes it very difficult. Dynamic objects and different densities are also different challenges. So it's a very challenging problem, and it's consumed a lot of researchers in computer vision, robotics, and AI. Now, the idea is that if I can do that, I can solve the localization problem using vision. The previous example on like a robot, there was no vision, but here, this is an example that we can vision. Now, ultimately, we want to use all of them in one framework, but we can look at it piece by piece, and later, it is possible to combine them within one framework too. So there's part of the data that is geometric, and there's part of it that is semantic. By geometric, I mean appearance, color, although it's from light, but it's attached to the point that is a 3D point that we sense in the environment. Semantic is a way to give the notion to every point as we understand it. For example, I can categorize, I can segment the scene, say this is a car, this is a road, this is a person, this is a pole, this is a tree, this is the sky. If we have this, that will make it easier, because then I don't need to match road with the tree when I'm tracking. Obviously, a road should be matched with a point that also belongs to the road. So that's the idea. However, things are not perfect. Everything is noisy. The depth is noisy. The color is noisy. You have difference in illumination. The lighting can change substantially. You go to shades. It's sunny. Change of view. The semantics that are also coming from a neural network that is running segmentation are very noisy. Although in simulation or in some cases it can be accurate, but in general, they are imperfect. Now, if you think about the color and semantics as labels, the question is how to combine them. One natural way is tensor product. Now, we're not going to, again, dive into it, but if you have vector spaces with different lengths and you want to combine them into one giant vector space, you can use tensor product. For two vectors, that's just the outer product. It's everything with everything. You just multiply every point number in the first vector with the other vector. So that gives a way to combine them. And if the inner product for overall space is just the product of individual inner product for each vector space. Now, from kernel methods, we know how to construct functions from data points. And that goes sometimes under the name of kernel density estimation. You might have heard of this. Basically, these can be Gaussian kernels. Some Gaussian kernels, like this, can be centered around your observed points, and then take weighted sum of all of them and normalize it. That will give you a function. Now it's continuous. Each of these bumps are a basis for your function. Then instead of matching points, which was common to do it, and we're not covering here, take the inner product between two functions. Now, one of these functions should rotate and translate as the camera moves. This gives a function view of the registration problem. The beauty of it is that now we take color, semantics, and points into one single function. It was not possible before. The framework embeds all the information in one place. And as a side note, this inner product, you can think about it, we're just maximizing the cross correlation between two signals. These signals are reconstructed from data. The data here is spatial, it's from 3D images. And we evaluate the cross correlation at 0 lag. It looks like a lot like convolution too. This is the shape of this inner product. And this gives a surprisingly better results than previous method was to search for what point corresponds to another point in between the two clouds images, and then minimize some distance between corresponding points. In this method, we don't need to search for correspondences. It is correspondence free. So again, this is very high level. But when we do that, which is also equivariant, because the same transformation that is rotating points and translating points is also rotating and translating these functions. It preserves that structure that I talked about. If we just accumulate frame-to-frame tracking, we can get results like this that looks very compelling. We can recognize the road and tracking. So this is just using a stereo camera on a car. It's moving on a highway, and we are tracking and reconstructing the scene. This is a larger view of that, and you can see a video of it. So the key message here is that I can use color, I can use these semantic labels, and I can possibly use other labels if you give me more information into one single representation of this 3D data. And then I can look at cross correlation of these signals over time and track my camera. This is another way of solving that localization problem. But also it gives you a map because you can visualize the map. I don't know if you have time, but this is the last few slides for talking about a navigation problem. So another flavor of problems in robotics is, well, how to plan. Let's say I know where I am, and I'm seeing a bunch of stuff around me. How to decide where to go. It isn't that the value of going into any place is equal based on the task and based on what the robot knows and what doesn't, which is encoded into that word model. It matters what's the next best place to go. So that's the problem of maybe exploring, maybe searching for an object, or maybe accomplishing some tasks. So generally this falls under the planning problem. One particular problem is that how can we use all the signals on the robot, the map that we talked about, the IMU signal, proprioceptive signals, into one framework so that we get a reward map. We have a value function in the sense of optimal control and Bellman equation, that there's a value function that will tell us what's the next best action policy. So it turns out what we can do, we can use neural networks to solve this. This goes under the name of deep reinforcement learning. Given data, learn a network that will give you a reward, and then you can solve it. Now, the problem is this is the inverse of that problem, because I don't know the reward function. So in reinforcement learning, we know the reward map. In inverse reinforcement learning, we don't know the reward map. Nobody knows what's the right value function to describe everything that the robot is seeing in the real world. So this network will learn this reward map, then we pass it to the robot to execute it and see how it goes. And that's how this training process goes. Now, what's the problem? The problem is that what people commonly implement, it goes under learning from demonstration. Let's say I grab the robot, use a remote controller, and drive it around, and then I collect data. Later, we will set up that environment to train the neural network by finding a reward map that when we roll out the simulation, it will generate a similar trajectory to the teacher, to when I drove the robot. Now that sounds very compelling, except the human who manually drives a robot has no idea what's the optimal policy. I do not sense what the robot is sensing. Where I go is purely based on what I judge. Maybe I have a sense the robot will fall if I go to left, then I go to right. But I don't know if that's the optimal trajectory. So the assumption that demonstration, the teacher is the optimal performer, is not satisfied. Therefore, the performance is suboptimal. So what we want to do, we want to get inertial features from the interaction of the robot with the ground so that we know how much energy the robot is consuming, then rank different trajectories, different policies based on energy consumption. Now, once we try to match the teacher, we have a suboptimal way of operating. Next, I want to outperform the teacher. I want to be better than my teacher. To do that, I need a value system to rank them. The value system here that we have naturally for physical system is the energy they consume. This is not possible in an Atari game because who knows what's going on. But on a robot, on a physical platform, we can talk about the energy that the robot consumes. So the trajectory that is closest to the teacher's demonstration and consumes the least amount of energy, that's the best one. And that will outperform the teacher because the teacher's demonstrations are suboptimal in this case. So that, if you run that, that will give you things like this. The red, if I'm right, is part of the trajectory from the past. And then we query where I should go. Then the network gives the cyan path. Follow this path. Again, red and then cyan, the third example. So what is nice about this is that now I can generate reference trajectory for the robot to explore. And that considers what the robot sees around itself, but also the information from interaction of the robot with the ground is included in that. So that was a problem in robotics because the amount of signals that we receive can be very large. A point cloud from a depth camera can have 300,000 points. Looping over 300,000 points in real time, that's already too much. Combining them with other signals, that's almost impossible. So this is a modern way of solving this signal processing and feature learning problem for this navigation problem. Now, one question is, okay, these different problems, how they fit in together? How are we going to make an autonomous robot once we have different modules? Well, the learning part creates some sort of memory for the robot, because there are hard to estimate quantities, just like that value function, just like contact events, maybe train types or friction. It turns out with machine learning, we can learn them. And then there is a way of tightly connecting them to an state estimator, or I'm not showing it here, but a reference from planner can be combined with a model predictive control. That's a controller that a lot of self-driving car companies use. We use it on the robot, and it's used on drones, quadrupeds, and so on. So what happens, we can enforce constraints using something like MPC, which guarantees safety, for example. A lot of safety critical applications that use model predictive control, they enforce safeties using, for example, control barrier functions. So you don't hit obstacles, or you don't go to part of the scene that is dangerous. The learning enables adaptivity. These two objectives are robustness and safety, and adaptivity. They are not usually, they're competing objectives. So with learning, we can be adaptive using memory. So the memory will assist making better decisions online. Robustness is from geometry, and safety is from satisfying some geometric constraints, because these learning methods do not understand the physical constraints of the robot at this point. So the result of that is enabling environmental awareness. Traditional approach to robot control was model-based. People would write down very difficult mathematical equations, and that would be it, encoding it. But now we can combine it with signals that we sense from the environment. That's how we operate. I look at you, I see you bored, then I change the topic, go to the next topic. I touch the table, I know what I'm seeing, what I'm touching. So these features for the robots are very important, and we just started understanding how to combine them. And that has become very important. Now, there is still that mathematical side of it, that if we understand the symmetry, how to use proper models, we can make this method so much stronger. That will make them to generalize. And that's the edge of research right now, bringing rigorous math and symmetry into methods that work well, but they don't generalize. And that's what we need in robotics and autonomous systems. So with that, I want to thank all the people who actually did the work, and I'm presenting their hard results, their hard-earned results here to you, my wonderful students, and thanking my sponsors.
Excellent, excellent, excellent. Thank you very much. Open it up now to any and all questions. Let's see.
I see one question.
Really silly question from me.
Yeah.
What's your favorite project that you've worked on?
My favorite project. My favorite project is, now this vision framework is a result of a bigger framework that I built with some math collaborators. I really love that work because I was trying to solve it for 2 years and I couldn't. And then I collaborated with some people, and finally they told me what was wrong with it and we could solve it. So I really like it, and my students are building on that. But my favorite work is the work that has rigorous math, it has open source software, and it works on the robot. If it doesn't work on the robot, I don't want it. So that's how I narrow my projects. Now that I can get rid of a lot of work that we shouldn't do, even though it's possible to do. So you must work on the robot in real life. That's how we know we should pursue that direction. But also it needs to have math. By math, I mean a reproducible foundation, something that people can learn it and reproduce it, although they can relax the assumptions and maybe change it. So any work that falls into this area, I love it. And it must be open source. I want other people to look into what we did, tell us what's wrong with it, or maybe they find it useful and they can run it. Hope that's a silly answer to your great question, not silly question.
I think that was a good question. So do you find your instrumentation limited in certain, or what are your processor speed or instrumentation needs of the future?
So that's a good question, because the computation resources are always limited on the robot. That's the problem we have. And a lot of algorithms in the lab are for the next 5 years, the future. We try to make them fast, but they look into the future when everything is faster and we can do more. So what we have right now, something like these compact PCs by Intel that you can buy. I forgot, Nuke computers, or NVIDIA has some Jetson embedded boards that we can have, very lightweight GPUs that we can use. And we have a tiny battery on the robot that we can operate with that. Something, you can imagine something like this phone, but a little bit better. I mean, a phone from 2022, not old. But what we need is more computation, or maybe revisiting how to work with that. I'm taking for granted all the advances in hardware, sensing, mechatronics, building these sensors, building the robot, integrating it. So I'm creating the platform and building the algorithms and making it autonomous. But I should acknowledge a lot of work that was done there, and we still need more work to be done.
Very good. In the chat, let's see, there was a question a little bit ago about, is it possible to label a specific leg? And I'm not clear on whether that was pointed at a graph or...
I have to make a guess. I'm guessing,
yeah.
The question is asking, can I say that it's contact for this leg? Yes,
Oh,
and that's what we...
For the point contacts.
So let's say this is 1, you can see it 2, 3, 4. The neural network tells me a label that is, let's say, false, true, or 0, 1 at any time for every leg. If we have 8 legs, then we will have individual labels for all of them.
Very good. Very good. I think that makes sense. And no, thanks for the clarification. Yeah. And thanks for the, yep, good chat in the comments. So the other one Taylor just posed is, are the point clouds stored for future use, or are they temporarily stored, or?
That's a good question too. Now the question is, you get all these point clouds, and what are you going to do with them? There will be a time we're out of memory, right? So we can't just keep storing point clouds and going, and these are actually expensive to store in memory as well. So that falls into, once you can solve this, and then you might want to turn this into a system that can operate for a long time. Then maybe we need to look into downsampling, maybe map compression methods, maybe more efficient data structures and removing redundancy, or maybe not storing everything and turning it into a lower dimensional just trajectory of the robot, for example. But this is a problem because we can build dense maps, but we're going to be out of memory. And that's why in computer vision and computer graphics, you see very impressive results when they reconstruct an object or a scene. we can't use that for the robot because one, they're computationally very intensive. Two, they only do it for a room level or object level or offline when Hollywood makes an animation that's running for months to build that. We want it on the fly, on the robot. So that's a problem, that's a challenge, building maps in long term.
Bruce, thank you for raising your hand.
Yeah, so hi, Mani. Thanks for the exciting talk. Yeah, it's really a nice layout of the work. So I have a question, since we're on this topic, just like the picture that I'm showing now, are you actually downsample the point clouds, or are you using the full point cloud? And how many scans of point clouds that you are trying to use in this framework?
Well, I'm the co-advisor of Bruce in Michigan. Good question, Bruce. So the point cloud is, as you pointed out, we are not using the entire point cloud, although we are visualizing the entire point cloud. We are making the point cloud semi-dense. We use maybe 3,000 points to 5,000 points for solving the problem, but to visualize the map, we're using all of it. Does that make sense?
And how, so you just randomly downsample the point cloud, or you have some, use some technique to downsample?
We tried several ideas. Random is an option, but for this work, we use fast features. You can use computer vision libraries like OpenCV, extract them. There are other ideas too. I used edge detection from Canny edge detection. That's another way to get points.
You said fast feature for point clouds?
For images, from images. These are RGBD or stereo images.
Oh, okay. I see. Okay, thank you. Yeah.
My students attacking me in public. That's.
No, I'm not attacking.
No, it's a good question. I'm joking.
Because I'm, working on
Paul.
Yeah. So very nice presentation. I have a quick question on the inverse reinforcement learning. You said that the reward, because you do not know the reward a priori, you're actually trying to learn the reward. And so I'm just trying to, I just lost you there. So is the reward the path that you showed with the garden on the side? So it's is that, how does it know that that is what you want? Basically, because of the initial trajectory that you allow the teacher to walk the robo through? Is that what you're trying?
The reward is the value function. It's the optimal cost to go, for example, right? That's the optimal cost in the sense of Bellman equation where we have reward function.
Right. In physical terms, you said that the teacher walks the robo through, and then is that how it kind of learns what it needs to pick up as the reward?
So the reward is that we have the trajectory of the robot for some time.
Okay.
And for that, we record data. There's a map that we build, height map and elevation map we build around the robot and the IMU signals and so on. Then what this solve RL is trying to do is trying to use that reward map to solve the value iteration problem. When we solve that value iteration, that will give another trajectory. Then we try to get the distance between the predicted trajectory and the trajectory we recorded using manually driving the robot. Now there will be an error in the top view, we can imagine. That error will get back propagated to the neural network to update this reward. Now, until this reward will be something that will match the trajectory of demonstration, it will be trained, it will continue. But does that make sense?
Yeah, so the confusion is, I think, if it sees a new path, data that it has not seen before. So I'm just trying to relate it to the physical aspect of it. So let's say that there was a pedestrian walk through which it is going, there's gardens on either side, you're training it for that. And then when you let it loose, then it is going to pick a pet walk with gardens on the side, typically, to continue its trajectory. Is that correct?
Probably hard to predict, but you're pointing out a fundamental problem, because these networks, deep learning, overfits usually to data, and then they cannot generalize. And that's a problem, because if we try to replicate the examples that we have, there's a concern that when we have a non-expected situation, this reward map is not capable of explaining that situation, such as somebody blocking, although here we're not dealing with dynamic objects. That's why we need this ranking. So just only replicating what teacher did is not enough. I need a method to judge what trajectory is better than another, regardless of what the example is telling me. That will help me to generalize. If I know that, then when I'm facing a new situation, I have a way of ranking and judging that's internally built into the reward. Now, that's a very difficult question to answer, but one simple answer is something we have in robotics, and that's the energy consumption. I think dynamic objects is a good future direction. We did not explore this. I don't have an answer for that, but hopefully that cleared why this might work in unexpected situations. It's because of the ranking strategy.
Okay, great. Thank you.
Hello. Thank you for interesting presentation in the robotics. I have just a simple question. You showed the legged robots, right?
Mm-hmm.
And those examples you use, do they have a constant leg stance or leg motion, regardless of the, where they are or condition of the floor?
So that's a good question, because now this robot, as it moves, it has some predefined gait cycles, different types of walking. Let's say 10 different ways of moving. Now, I think your question, if I understand correctly, is there a way that based on the interaction with the environment, I pick the gait that is the best?
Right, or like this study included that, that online active control of those stance as well, or it's based on the uniform stance? Yeah.
We do not change the gait. Your idea is really great. If somebody can do that, that will be a very good and new results in this area. If you can manage to actively decide what's the best way of, moving the legs or navigating, changing gait, that will be great. But right now, for us, we just pick a gait and then use that. Although for the training data, we try to use different gaits so that it works with whatever gaits we choose online.
Okay. If that is the case, then we might need another object function to control it, right?
I think so. I think we need a way to quantify the configuration of the robot based on different gaits, how it will dynamically contribute to having that better reward, for example, for navigation, because that will affect the energy that we use for ranking. Maybe there is another gait that consumes lower energy. Suddenly that will be better.
And then one follow-up question is, like you showed the example of using invariant extended Kernel filter, right?
Mm-hmm.
And how is the computation efficiency of that method? Is that like light enough to run, online?
It is extremely efficient. It's just like a normal Kalman filter. No more expensive than. It's the same. It's like quadratic cost because of rectangular matrix multiplication. So we can run it on by Cassie bipedal robot at 2 kilohertz, 2,000 times per second. And on other robots, we can run similar to that. And you can run it faster too if data comes faster. That's the limit of the joint encoders. So it is very, very efficient. That's why it makes it attractive for an observer.
Okay. All right. Thank you.
Thanks for the questions.
I think that was, well, certainly very well done. I was just pausing to see if there were any last questions, but certainly thank you very much. Very clear, very interesting, and certainly, you know, shows a lot of us that don't have a lot of background in the mathematics of the robotic, you know, technical issues. Was very, very informative. So thank you very much. I don't, unfortunately, Zoom meetings don't end with nice clapping or unified anything other than waving at your computer screen. So I believe we are clear to wrap up. Again, very much appreciated. It was very clear, very well done, clarity and everything about it. So with that, any last notes or comments or words of encouragement, Manny?
Thank you. It was a pleasure getting to know you and giving this talk again. I wish it was in person, and I hope in the future we can meet in person.
Mm-hmm.
And if you have any questions about any part of it, it doesn't matter if you're curious or you just want to have questions, feel free to contact me or any of my students. And that's it.
No, it's very impressive, and certainly, you know, you see a lot of applications for them, from onshore with legs to offshore and ocean engineering to a variety of different remote capabilities. So thank you very much. Very informative. Thanks,
Thank you.
everybody.
Bye.
Very well done.